Hello everyone, welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. In the previous video we discussed a little bit about TLC 555, which is a special kind of 555 timer integrated circuit that has some benefits over the other ones, the standard ones, let's call them this way, and NUA, SA 555, and we have taken a look at what those advantages were. Today we kind of make one step further and we see how we can use that 555 timer to basically create a rather primitive but still good enough DC to DC converter that steps up the voltage. The 555 timer is definitely not the best integrated circuit to use for any form of switching power supply, but it still can be used. It gives, let's say, decent results in some conditions, so why not? So I'm in the process of creating something bigger, some accessories for my oscilloscope, and I want, I'm in the process of creating some differential probes, essentially some custom do-it-yourself differential probes, because the ones on the market are just way too expensive. Like, even the cheapest ones are way too expensive and I need more than one. So the thing with these differential probes that I want to build is that I want them to be powered from batteries. However, a battery, even a 9-volt battery, is not really enough, not good enough for what I need, because I'm gonna need to power some op amps with a considerable amount of voltage, so that I don't have to attenuate the input signal so much, so that the smaller signals can still be visible relatively easily. So for that I need my differential probes to be powered from a voltage that's higher than the usual voltage that batteries have. A single 9-volt battery is not good enough. Two of them are still not good enough. I would have to use 3 9-volt batteries in series, and that's kind of an awkward solution to choose. So the best idea that I could have is to use a 9-volt battery to power what's called a boost converter, or a step up DC-DC converter, right? So I wanted to have one of the simplest boost converters ever. So I decided to try a 555 timer to generate a square wave, to control some switching elements and generate this higher voltage. And this is exactly what I did. I also wanted to have some sort of feedback mechanism that would kind of make the 555 timer turn on and off, start to oscillate or stop oscillating for a certain amount of time based on the output voltage. And this is easily possible because the 555 timer, all versions of 555 timer have a distinct pin that is the reset pin, and it works in reverse. In one logic it doesn't do anything, in zero logic it does the reset function. So basically it's in reverse, right? We need to pull the reset pin down to the ground in order for the reset to happen. So anyway, this is basically what I present to you today. You have the schematic in front of you. Just ignore the title, which is obviously not in English. Just ignore it. It doesn't matter for now. What we have here is probably the most primitive form of a switch mode power supply, more specifically a step-up converter. Okay, I say the most primitive form, not the simplest form, because it still has quite a few components around, and in today's market we definitely could find some very specialized integrated circuits that need very few components outside of them, because they do pretty much everything inside. But I did not want to search for something like that, and I typically will not want to use something like that, because that forces me to buy integrated circuits only for that specific purpose. And overall, I would like to use as many basic components as possible. So anyway, this is the schematic, and this is the reason why I chose a 555 timer. In essence, we could just split the whole schematic into two pieces or two parts. You can just draw a vertical line in the middle of the schematic. Everything on the left is just a 555 timer in astable mode, so that it generates square wave constantly. On the right side we have the switching elements of a boost converter. Okay, we have a couple of low power MOSFETs, 2N7000s in my case. We have a couple of inductors here, 1 millihenry each, and some diodes to steer the current around. I chose 2 stages, each stage having her own MOSFET and inductor, because I need to get up to at least 30 volts, and with just one inductor that wouldn't be enough. So I needed to have 2 inductors that I would charge. I would basically excite in parallel, but then I would allow them to discharge in series, and in this way I am creating a higher voltage. And in between these two halves, the half of the circuit that generates the control signal and the half of the voltage that of the circuit that takes this signal and switches on and off to produce the higher voltage, we have this semi-adjustable resistor R5, 100 kilo ohms in my case, connected to T3, which is the third MOSFET transistor, also 2N7000, which basically pulls the reset pin of the 555 down to the ground. There are plenty of videos on YouTube about 555 timers and how to make them work as astables. Many times, for some odd reason, people call it astable multivibrator. I don't understand the part with multivibrator. Like, why would anyone feel the need to say that this circuit vibrates? That's just, I don't understand. Anyway, I'm just gonna simply call it a stable circuit because that's what it is. It's a standard circuit that you can find pretty much everywhere, so I'm not gonna be talking a lot about it. From my previous tests, I have established that using 1 millihenry inductors and these transistors, well, actually more like just the inductors are the ones that dictate the frequency and the duty cycle. I need to have a signal that switches them on and off of about 100 kilohertz. It doesn't need to be 100 kilohertz sharp. It can actually be anywhere between, I don't know, 40, 50 kilohertz and 120, maybe even 130 kilohertz. So anywhere around that frequency is good. And also I need to have a duty cycle of about 70% in order to get the absolute most out of these coils. So the 555 timer with R1, R3 and C4 are exactly doing this. They are generating a signal which for me was about 85, 86 kilohertz and of about 71, 72% duty cycle. I have R2 which pulls the reset pin to the positive rail, so that normally the 555 would continuously generate control signal on the output. And I also have a C3 decoupling capacitor on pin 5. This is not a critical value to have. You can have anywhere between, I don't know, 10 nanofarads upwards. Some people might even choose to just not place this capacitor at all. R2 resistor is also kind of, it's not optional, it's mandatory, but its value it's kind of up to you. I suggest placing a relatively high value here so that the current that flows through it when T3 transistor pulls the reset pin to ground is not too high, and it's not, you know, just wasted current. R1, R3 and C4 are, however, components that must have this particular value: 18 kilo ohms, 12 kilo ohms and 330 picofarads respectively. Okay. So let me draw something on top of the schematic to explain a little bit better how this circuit works, and then we will go to the workbench and I will show you in a very concrete way how this circuit works and basically what to expect from it. Keep in mind that this particular circuit is good enough for very low currents. Okay, so in my case, like I said, I need 30 volt output and the maximum current will be around 10 milliamps, which is really low current. But I won't be needing more because I will be just powering a quad op amp, which is about 10 milliamps of current it draws from the power supply. For bigger currents we need different kind of circuit with better components, and yeah, so bear in mind that this is a very rudimentary design. It's good enough for very low currents, and therefore it tends to be good enough for you know, all sorts of lab devices and accessories, but it's not good enough for other projects. So let me start to draw some things on the schematic. So like I said, the 555 timer generates square wave signal with some 70 something duty cycle, and if it would be left alone, it would generate the signal continuously. Now, this signal is fed through R4 resistor, which is around here, into the grid of, or into the gate, I should say, of these two MOSFETs. And essentially the 555 timer is turning hard off and hard on both of these MOSFETs at the same time. Okay, the R4 resistor is chosen more or less arbitrarily. I chose a value that I don't use so often, but a relatively low value. Now, when these two transistors are turned on, and they are turned on hard, they become almost like a short circuit. And they basically pull these inductors down to the ground. In that particular moment, a current will start to flow slowly through each inductor, and each inductor will start to create that magnetic field around it, okay, which is typical for inductors. When the control signal gets pulled low and it closes these two MOSFET transistors, due to the nature of any coil and any inductor, those two coils, L1 and L2, will want to oppose this change in current, and therefore they will want to start pushing their own currents in the exact same direction as the current flowed before that. So when they will want to generate their own current, they will essentially be creating a voltage across them, which will be in reverse. It will have the plus here and the minus here, okay, in both cases. The diode D2 will start to conduct the current, because, you know, the current flows in the same direction as it allows it. The diode D1 will block the current, because the current will not be able to flow backwards. The diode D3 is also going to allow the current to pass through it. So basically what we have here is a combination of three voltages that are basically higher than the input voltage. These voltages will always be higher than the input voltage. And as a result, the output voltage will be higher this way. So we have the voltage across L2 coil, plus the voltage across L1, plus the voltage of the input source, whether it's a battery or a power supply, whatever. So we have the sum of all of these three voltages minus a couple of voltage drops on these Schottky diodes. And this whole larger voltage, okay, will be across here and will charge C2, which is a filtering capacitor, or a bulk capacitor, how some of you might call it. And at the same time, this will be the output voltage, okay? Now, if 555 timer would be to constantly generate this control signal, this square wave, then the output voltage would rise really quickly, and it would rise to potentially harmful values. Okay, a few things to take into consideration when you're building such a circuit. One is the maximum working voltage of the output capacitor, C2 in our case. It needs to be high enough, ideally higher than the output voltage. Worst case scenario equal to the output voltage, but that's not really a good idea. The third thing that you must take into account is the reverse voltage that each diode will see, because Schottky diodes can only withstand a certain amount of voltage, which is kind of always low voltage. In my case, I chose SEBE 130. This SEBE prefix comes from the word Schottky barrier. So basically these are Schottky diodes, okay? If we apply more than 30 volts, because the 30 from SEBE 130, the 30 designates the maximum reverse voltage across each diode, okay, which is in this case 30 volts. So if I were to have on the output a significantly higher voltage, that would make it so that on each diode the voltage would be the reverse voltage would be higher than what it can withstand, then I would overall have a problem. You know, because this diode might break, or it might just start to conduct current in the reverse direction as well once this voltage is taken above the limit. So this is the second thing that we need to take care of, choosing diodes with a reverse breakdown voltage higher than what's possible in our circuit. Third, but not least considerant, is the maximum drain to source voltage of these MOSFET transistors. Now, the first transistor only sees the higher voltage that the first inductor generates. However, the second transistor sees the entire output voltage between its drain and source. So it is very important that we never make this circuit oscillate so that it generates a higher voltage on the output than these components are able to withstand. Okay, so in order for us to prevent this from happening, especially when we don't have any load connected to the output, in order for this not to happen, we need to shut down the oscillator from time to time. This is what happens with this transistor T3 and this resistor R5, which is an adjustable resistor, or a potentiometer, if you want to call it this way. Basically, when the output voltage increases over some amount, over some value, the voltage across the lower portion of this potentiometer also increases, because as we know, This is the nature of a potentiometer. It gives us a ratio, a fraction of the total voltage applied across it. And if this voltage, if this fraction is high enough to open T3, because this fraction of a voltage is applied to the gate and source of T3 transistor, then T3 will open and it will drag the reset pin to ground, which will cause the 555 timer to stop oscillating for a while. Okay, and we might see something like this, which is a flat line for a while. Meanwhile, the voltage here at the output will decrease a little bit because R5 acts as it also acts as a small consumer, a small load. Okay, so when the voltage across C2 capacitor, which is also the output voltage, drops below a certain level, then we will no longer have enough gate to source voltage for T3 to remain open, and it will close, allowing the R pin of the 555 timer to go up towards the positive rail, which will cause it to start oscillating again, at least for a short while. We might be able to see something like this. Okay, and after a while, of course, the voltage on the output will increase again over a certain threshold. T3 will open again, it will pull the reset pin to ground, which will cause the 555 timer to stop again for a while, and so on and so forth. So the whole story repeats over and over and over again. Okay, and this is basically how this boost converter works. This boost converter has an efficiency of about 75%, at least at these lower currents being drawn from it. It's not bad, but it's not good either. Okay, it's acceptable for some projects. And this is the reason why I'm creating it. This is the reason why I'm presenting it to you as well. So, with that being said, I think it is now good enough moment to go to the workbench and basically show you exactly how this circuit works. I have the circuit on a breadboard, and I have two multimeters that measure the input and output current, as well as an oscilloscope that shows us the control signal in blue and the output voltage in yellow. So just allow me to go to the workbench and I will start explaining, and I will start changing some things around so you can better see how this whole thing works. Okay. Okay, so what do we have here? Well, we have, like I said, two multimeters. This small black one measures the output current. The yellow one measures the input current. I have outside of the camera a power supply that feeds this circuit on a breadboard, this boost converter, and on the output I have an electronic load. Okay, that electronic load is the one drawing 10 milliamps constant current. I also have the oscilloscope in this corner of the screen, which shows me in blue the control signal that 555 timer generates, and with yellow I have the output voltage. Bear in mind that I have 2 volts per division for the blue signal and 10 volts per division for the yellow signal. Okay, so make sure how you compare them. Also, do note that I've dragged down the 0 line for both channels. It's here now, so I can have more space upwards because my signals don't really go below 0. Okay, so right now I have about 5.6 volts on the input, and you can see this here on the oscilloscope where it says peak. Okay, peak value. The peak value of the control signal is very close to the supply rail, the positive supply rail, because the TLC 555 integrated circuit has an almost rail-to-rail output. Okay, so I will start to change all sorts of things, and as I will change the input voltage, you will see that the control signal will go up and down. Okay, while the other signal, the output voltage, might not do anything. So I need to have a minimum of 5.6 volts in order to have about 30 volts on the output, and at 5.6 volts input, the 555 timer is required to oscillate quite a lot. It's required to oscillate at 86 kilohertz, which is the actual frequency that I've set for him, and it oscillates constantly. It never takes any break. Okay. However, if I start to increase the input voltage, we will see that the control signal will start to bounce around a bit. And the reason it's doing this is because, well, now it doesn't need to oscillate at 86 kilohertz constantly. Okay. Now that feedback mechanism with that semi-adjustable and the extra transistor will start to kick in, and for short amounts of time, from time to time, it will kill the oscillations of the 555 timer, so that the output voltage remains pretty constant, okay, around the level that we set it beforehand. And I'm going to keep increasing the input voltage. I have now 7 volts, a bit over 7 volts. Okay, now I have 8.1 volts on the input, and we see that now all we need to have is a 36 kilohertz signal with about 42-43% duty cycle in order to have a 30 volt 10 milliamp on the output. Okay, and if I keep going upwards with the input signal, you will continue to see this trend going on of the boost converter needing to switch the inductors less frequently, okay, in order to keep its 20 volts output voltage. On the other hand, the opposite is true. As we minimize the input voltage, the whole circuit will have to start working more and more and more until it reaches its maximum. And if we go below that minimum input voltage, we will see that the output voltage is no longer able to stay there at 30 volts, and it will start to decrease alongside the input voltage decrease. Okay, provided that we are insisting on drawing the same amount of current from our boost converter. Okay, now let me show you something else. I will set it to 20 volts only, output voltage. And I will decrease the current that I'm drawing from it. So I'm going to play with the electronic load that I have outside of the frame of my screens, of my cameras. Okay, so I'm going to adjust the current down yeah, no, nothing's gonna happen because I've set it for 30 volts. Yeah, sorry. Okay, so okay, here's what we will do. I will set the input voltage again so that is enough for 30 volts. Okay, and now I will start to decrease the current, the output current that I'm drawing. And we see the exact same phenomenon that we have seen earlier when the 555 timer was killed for some period of time, and therefore instead of having 70+% duty cycle, we now have something like 26-27% duty cycle for our control signal, because that's just enough for 2.5 milliamps output current in order for the output voltage to remain constant at that 30 volts. Okay, and as I decrease the current that I draw on the output, the impulses become shorter and shorter and farther apart one from another. And if I remove completely the electronic load, then I see that, well, I have impulses that are so far apart one from another that the internal frequency counter of this oscilloscope consider this signal to be about 2 kilohertz only instead of 80 something. Okay, so yeah, that's how this thing works. Now, with the electronic load disconnected, let me show you what happens if I want a lower or a higher voltage and I adjust this semi-adjustable potentiometer from my circuit. Okay, while keeping the input voltage constant at some 5.6 volts or so. So if I want to have an even smaller voltage, then these impulses become even more spaced apart. Okay, this pseudo frequency that this device is measuring has dropped because the distance between these spikes has increased. Okay, if however I want to increase the voltage on the output, these spikes become more and more frequent because they are needed to be more frequent. in order for me to have a higher voltage on the output and to maintain it there. Okay, so now we have 40 volts on the output, and I will take this to 50 volts. The circuit can go higher, like 60, but I'm not gonna go above, because I'm basically gonna have a problem with my capacitor and my diodes. Okay, my capacitor is rated 50 volts, and now I'm at 50 volts output, which is the absolute maximum from this capacitor. Okay, I'm gonna turn it down to, let's say, 30 volts again. What do I show you? Oh, yeah, I'm gonna connect the load back, and I'm going to slowly increase the current to show you how these spikes become more and more frequent in order for the whole circuit to maintain stability. Okay, 2 milliamps, 3 milliamps, 4 milliamps, 5, 6, 7, 8, 9, 10. Okay, so if I remember correctly, I've just shown you everything. I've shown you the influence of the output current over the input current, and well, over the whole circuit. I've shown you the influence of the input voltage, and I've also shown you the way that this potentiometer on the circuit works. Okay, let me show you again. Now I have 30 volts on the output, 10 milliamps. The circuit is working at maximum capacity, but if I decide to lower the voltage from the potentiometer of the circuit, okay, let me see, then I get pretty much the same effect. Some pulses that are farther apart from each other. Let me pause so that you can see better. Okay, so we see that we don't need to switch all that often. Only a couple of normal excursions are enough in this amount of time, in some 25 microseconds, I believe they are here. And then we have another 20 microseconds or so of just not doing anything, and then again a couple of spikes, and then again a break, and so on and so forth. And if I lower even more the output voltage, let's say I make it 10 volts, why not? Well, at 10 volts, at 10 volts I need a couple of spikes, and then a pretty long period of time of just not doing anything. So I have 50, 100, I would say 120, 130 microseconds of just dead time. Okay. The problem is now this frequency is pretty low, at which it oscillates 13 kilohertz. You don't hear it, but I do. There's a very faint noise, high-pitched noise that I can actually hear that comes from the coils that the circuit uses because of this frequency. Okay, so yeah. And this goes away on higher loads. So yeah, this is pretty much it. Pretty much all I wanted to show you. I hope you found something useful. I hope you now understand a bit better how boost converter works, at least the basic principle. And I hope you now know how to build one, a very rudimentary one, if you need it for your projects, and your projects draw very small currents, like in the order of milliamps only. The nice thing about this particular circuit is that I can use consumed batteries from other devices to power this, because a 9-volt battery, when consumed, it will have its voltage go down even to some 6 volts or so. But as we have seen earlier, 6 volts are enough to generate 30 volts and have a 10 milliamp of current drawn. So that's a nice bonus we can actually use for this particular project of mine. We can actually use used 9-volt batteries. They don't have to be brand new. So anyway, I'm going to put this schematic up on Patreon. Thanks a lot for watching. I hope you found it useful and interesting. If you consider, please hit the like button and subscribe to my channel. I'm coming back with more videos regarding electronics world. And also, if you would like to support my work, feel free to do so on Patreon. I have link in description. The faster I can buy components and even lab devices, the faster I can learn things, and I can come here and teach you as well, so that you don't have to bother wasting your time and energy with all of these things, so that you can just come here on this channel and find schematics that have been tested by me and that are known to work, and you can just take them and use them and create them for yourself. I will soon come back with more videos regarding this small project of mine of building a differential probe for my oscilloscope, so stay tuned. Thanks a lot for watching. I'll see you next time. Bye bye.